I better record this because I promised. Okay, so, can you guys see? Is that screen okay? It's huge. But if it's, well, it should be big enough, right? Yeah. Okay, so just some notes before we kind of, well, housekeeping, let's call it. Like I said, I'm available all day on Wednesdays, and so, well, one, if you have questions, whatever, but if you do, as a group, decide that you want to move it to this time, I'm fine with that, but I'm going to leave that with you because I don't want to be the one who's like, no, we're changing class again. I know. And so, but also we've got your quiz 2. Oh, man. It's really hard to write on here, but I'll get used to it. Quiz number 2 next week. What? I know. Surprise. Wait, I thought I posted the quiz dates.
No. It just says a week something.
Okay. Okay. So I'm like, okay, well then it's yeah, whatever we've covered since the last quiz. I didn't have a chance to run through all of it. Like I said, like I usually have until 3 to look at stuff, and so now 9 kind of made me work double time, but so I didn't get a chance to look at all of it, but there is a little bit of overlap just because we have talked more about null hypotheses and what do we do with p-values and things like that, right? So, so there's a little bit overlap from the first quiz, but those should be gimme marks now, right? So that's why I want to keep them in there because I think that you'll find that they're a lot easier. If you want to go through your first quiz, oh, sorry, yeah.
It says in the syllabus it's week
11. And what week is it now?
9.
9. Putting it in 10. Well, I don't care. It's just, yeah, do you guys prefer to have it in week 11?
Can you talk about what's on it first more? If it's anything like the group project, then no.
No, it'll be multiple choice again on Moodle. So it'll be same setup as last time. So a lot of, like, the questions are from the textbook, right? So not the ones that you have, but the textbook kind of sends them. And so they'll be very kind of similar to quiz 1. From chapters, yeah, is it 7, 8, and 9? Did we do 4 and 6? That was last quiz?
1 to 6, I think.
Okay. Yeah, so 7, 8, and 9. Chapters 7, 8, and 9.
So if we were to move later, we would learn 10 and then have to do the quiz on 7 and 9. That confuse anybody?
Yeah, so if you want, I could put 10 on there on the quiz. I mean, fake though, like the easiest questions I could find from 10, and then we'd all be legit, right? Because it's hard to keep track of like new material, old material, like study, this is on the quiz, this isn't on the quiz, right? So at least if everything that you've seen up to that point is on the quiz, then that I think that's helpful, right? Because then you don't have to keep track of, oh, well, this was new, or this was, yeah. So, so what we could do is, oh, I know what happened. I had us spread out because we had those extra days. And then now, because we're doing the final exam in class, I just scoot them back. So that's why I was like, why is it weird? But that makes sense. happy to do it either week. Just let me know. Again,
What chapters would the final be on?
all of them. Yeah, so it will be cumulative. And there's nothing I can do about that. But with emphasis on the newest stuff. Yeah.
The 13th, it will be 7, 8, 9, 10, but if we do it on 6 and 7, 8, 9.
Yeah.
But
And
10,
then we
like,
would have
not
3 weeks till the
Mhm.
final exam to study. Till the 6th.
We're only going till chapter 11.
I think we should.
Yeah.
Just next week. I think so.
You know, just
Wait,
split
it's
it up.
Yeah.
Mm-hmm. So keep it next week.
Yeah, because we have more stuff.
That's what I,
Maybe too much.
yeah. Yeah.
What's the following?
Just like
Okay, so we'll keep it for next week. I know, I feel like I'm always negotiating with you guys, but I'm like, hey, whatever you want to do. Oh, what's that? So we'll keep it next week. It'll be on 7, 8, 9, and then after that quiz, we're gonna do chapter 10. And so chapter 10 will obviously not be on the quiz, but after the quiz, we will go through chapter 10. And so, pardon? Yeah. Chapter 10 is not going to be a lot. There's nothing really new. So, well, it's new, but not really. It's on November 27th. Well, whatever the Wednesday is, the last week of November in class. So, and then just to put a note here, final exam in class. Do you guys have the date? I think it's the 27th. 27th? Yeah. Same thing. Yeah. So same setup. And I mean, like I said, you're welcome to stop by my office and we can go through your quiz. So just see what went wrong on the first one, on the second one, right? And then you'll have that under your belt, right? Because I haven't been able to make it available to you guys to review. So just stop by, okay? Okay, my handwriting is terrible, but I will post these notes on Moodle when we're done. So that's nice too. I know, I feel like I'm back to normal, except the writing bit like this is hard. Okay, that's enough housekeeping for one morning, right? When do we want to have the quiz? I don't know. Okay, so we'll keep the quiz next week. And then, oh. So, there we go. So, here we go. We just started, actually. Yeah.
Just like knocking, like shaking the door.
Oh no, I don't know. It's like a secret cave in here. It's fun, right? Okay, learning outcomes, blah, blah, blah. I guess I shouldn't say that when I'm recording. Learning outcomes, who cares? At the end of the class, you'll know what you learned. But anyways, we're gonna talk about chi-squared tests. So chi-squared tests are for categorical data, right? So last week we talked about t-tests specifically, right? Where we're comparing the means of usually two groups, right? We can compare the mean is the average, right? The mean of a group to some number, right? But usually we want to compare the mean of this group to the mean of this group, right? That was t-test. Now we're doing chi-squareds. So now we're talking categorical data. And so for categorical data, right, we're going to have categories that we're dealing with. So we won't be able to talk about the averages, right? The average gender, for example, doesn't make sense, right? And so the chi-squared test is for categorical data. It's also called a non-parametric test, just because there's no mean or average or anything like that. I put this review of hypothesis testing here. And you know what? I'm gonna copy pasta here, copy, and throw it into here. Because like I said, I'll post these notes. Okay. And also from what I saw of the quiz when I just had a quick skim of it, you will need to know the steps of hypothesis testing. So I figured I'd throw them on here, right? And so it's just going to be one of those kind of fun where you rearrange it gives you all the options and then you rearrange them and put them in the right order, right? So that's, I think, the only one that's not multiple choice, but anyways.
So would that mean we don't really have like calculation ones?
Well, like I said, so there might be calculation ones, but then you pick the answer for multiple choice, so there can still be some calculations. For example, we're going to do some calculations today, so maybe have those under control, right? But again, I'll just add to the formula sheet that I gave you guys last time, and so you'll have any formulas that you need. All right, so for hypothesis testing, right? Like we said last day, the steps are always the same. It just depends on what our data is, what our research question is. That's going to dictate what type of test we're doing, right? But the first thing that we're going to do is we're going to state our null and alternative hypothesis, right? And then we're going to say, this is the alpha level that I'm using, right? So define the significance level. You should probably figure out which test you're going to be using before you state your hypotheses, right? But also included in, oh, that's really nice and dark, or light, I should say. Can't really see it, but there's a Z test, not very common because we use a T test. There's also an F test, which you did or you've been working on for the group project, right? F is actually used in a lot of different situations, and then the chi-squared test, which we're going to talk about today, right? So those are your most common tests that you could do. Okay? What you're going to want to do too is, I'll just emphasize it here because it's really kind of light, but you have to check assumptions. Oops. And so once you pick a test, there's going to be some assumptions. A lot of them are kind of, I don't know, basic, like was your sample randomly selected? That's an assumption. If it wasn't, then you have to say it wasn't randomly selected, but I'm going to go ahead and assume that it represents the population. Right? And so things like that. And we'll talk about the assumptions for the chi-squared. Then you run your test, and usually we just use software, right? So software will just calculate our t-test, for example, and then it gives us a p-value. And then it's our job to be able to interpret that, right? Does that mean we can reject the null hypothesis or not? Yeah. And then you have to draw your conclusion, right? Do you have statistically significant results? Meaning, have you rejected the null hypothesis, right? So, and then I've got the two conclusions, but what I'll do here is I'll just clarify. Did you reject H naught, right? That's what it means to be statistically significant. Okay. Any questions? So we're going to do more hypothesis testing. I always, whenever I do hypothesis testing, I always want to sing the Sound of Music song. Do you guys know that when you know the notes to sing, you can sing most anything? That was my ditty for today. Oh yeah, yeah. Well, that works too. Yeah. I skip the assumptions, and so, and I kind of, for me personally, defining the significance level, step 2 there, I don't really count that as a step, but I have all 6 there, 1, 2, 3, 4, I guess I have 5 there, because that's what matches the quiz from what I saw, right? So I just want you guys to have those so that you can figure it out, right? Oh, because I wasn't, maybe you weren't here, but one of the quiz questions is it gives you these options and you have to rearrange them in the right order. Right? That's why I wanted to go through that. Yeah.
Okay, so we don't have to tell you
Yeah.
anything.
So the default alpha is 0.05, right?
So yeah, it hardly even is a step then.
Yeah, so, but then I could say use an alpha level of 0.01 or 0.1.
But you
or,
would tell us. It wouldn't be like we have to
Mhm.
base it on whatever.
Yeah, totally. Oh no, it would just be me saying, do this. All right, so stick this over here. Wait, page breaks, busting my chops. All right. So like we said, right, chi-squareds are to test categorical data, right? So I guess I have it here, right? But so between independent groups, so groups mean that we have categorical data. It also has when the outcome variable is at the nominal level. I would say, I would change that because it slipped under my radar, is at the nominal or ordinal. Remember the difference for category, because we've been dealing with numerical variables for so long, right? T-tests, averages, blah, blah, blah. So now for categorical data, right? Remember we have nominal categorical data, which is no order, right? Or ordinal, where there is some natural order to the data, right? Or to the categories. Okay. And so what the chi-squared test does is it says, okay, well, if our hypothesis is correct, then there's going to be expected values for each count in each category, right? And so each count will have an expected number or an expected count assuming the null hypothesis H naught is true, right? So what we do is if we have categorical data, right, is we make a 2x2 table, usually, because here we've got our category 1, category 2, and then we've got group 1 and group 2. it can definitely extend to more than 2 by 2 groups, right? And so this is a 2 by 2 contingency table. Okay. So each of these cells is going to have some count. Okay. So what the chi-squared does is, okay, if we assume that the null hypothesis is true, right, then we'll be able to calculate how many we expect to see in each of these cells. And then we look at the difference between what we actually saw and expected, right? And then we'll be able to say, well, if that difference was too large, then we can reject the null hypothesis, right? And we'll look at that calculation, but this is the idea. And for this course, we're only going to go to a 2 by 2 table, right? And so it's not going to be anything more. You definitely could deal with more, but as far as hand calculations go, you don't want to do that. And the bummer is that Excel doesn't really do chi-squared tests that well. It takes a lot of work, and it's just easier to do it by hand at that point. Okay. So, so that's a 2 by 2 table. So, oops. All right. So there's 3 common tests that we could use the chi-squared for. And so 3 common tests for chi-squared. Right. Oh, and chi, if you want to write chi properly, it's this very fancy x squared. Whoa. But these are the 3 common tests for chi-squared. I'm actually not sure. I'm sure they've used it for other things, but these are our go-tos. And in fact, this is the only one that we'll do in this class, but the others work in a similar way. Only one covered in this class. Yeah. So we're going to do a chi-squared test of independence. I've put each of the null hypotheses on here because if you're given the null hypothesis, what you'll find is that that gives you a really good idea if the test is appropriate or not, right? And so the null hypothesis for a test of independence is that there's no association between the 2 variables, right? And so what that means is these 2 groups are independent of each other. Being in one group does not affect the count in another group, right? And so it's exactly what the name kind of says, right? But you're just testing if 2 groups are independent. All right, and I'll put a little note here. Testing to see if the 2 variables we are comparing are independent of each other. Okay. So that means that, okay, if we're talking about you know, gender. So we've got males and females, and then they have a dog, they don't have a dog, right? That's a yes, no category. Right? What we would be saying is that the count in the have a dog groups for both the males and females are essentially the same, right? And the count for doesn't have a dog for the male and female groups, right, are essentially the same, right? And so they're independent of each other. So there's nothing to say that, oh, there's an association here, right? If you're a girl, you're more likely to have a dog, for example, right? Although I suspect that's true. But anyways, I have a dog. So, question or a stretch? They're allowed. Look. Yes. So another test that we could do is a goodness of fit test. It's very similar, but it's if we're expecting to see some proportion, right? So not necessarily that they're independent, meaning that all the groups are, you know, the same or proportional at least. So the goodness of fit is if we have some distribution in mind, right? Did our sample match that distribution? So it's a little bit different, and it affects our expected values, but not much else. And then there's the homogeneity, meaning are all the cells all the same, right? Thinking back to our 2x2 table, right? The homogeneity is just saying, are all these the same? So it doesn't matter what group you're in, right? They're all homogeneous. Yeah. We're not going to do that one. Like I said, we're only doing the test of independence in this course. But they all work the same way. And so once you've seen this one, you can find all the others. Any questions? So thank you. What was that?
So if this test is like for frequency of how many things happen, and you're like, why do you have to estimate what could be a frequency?
Because so we've collected a sample to see how our sample behaves, right? And we're assuming that that's a representation of the population. So what we're doing is we're going to see if that matches what we hypothesize is going on, right? So we've got this idea. For example, if I go back to, I've got this idea in my head that if you're female, you're more likely to have a dog than if you're male, right? That's my hypothesis. I'm going to assume that they're the same, right? So the number or the frequency of the males and females who have dogs is the same. Then I go out and I collect my data. I randomly select my data and I ask males and females, do you have a dog? 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 And then I compare those counts to what I'm expecting to see, right? Or rather, if they were the same, right, then we would assume a 50-50 split, right? And then if my data says, well, I'm actually not seeing a 50-50 split, I'm seeing a 75-25 split, for example. So we do those comparisons, but across all groups.
Okay, so are we always then I guess, are we always estimating that they are going to be the same or different?
So for all hypothesis testing, we always assume that the null hypothesis is true.
Yes.
And so we always have to assume that these things are independent, right? So this group or this variable is independent of this variable in this case, right? So we always have to assume that they're independent until we have proof from our sample that they're not. Okay. I'm going to seal this, but also write that down. All hypothesis testing. So this is any hypothesis test. Sorry. Is done assuming H naught is true. Right. We only reject H naught if the sample gives us evidence to. If that makes sense. Thought my writing would be nicer if I had a flat surface. It didn't. It's just harder. It's very harder. Did anyone not get the table? Who needs the table? Everyone else has one? So what you'll see, right, is the chi-squared table that I gave you. It needs degrees of freedom on the left-hand side. Okay. And so we're going to talk about how we find those, and then we'll talk about how to use the table, right? But we need to have degrees of freedom for basically any test that we do. Okay. So for a chi-squared, in your 2x2 table, well, I shouldn't say 2x2 table, but in your contingency table, and like I said, in this class, we're only going to deal with 2x2. Right? It's the number of rows minus 1 times the number of columns minus 1. Right? And then there's this cute hint that was in the note. Oh, it doesn't really show the highlighting on there, but I highlighted the psst, which I thought was really cute. Here's a hint. All 2x2 tables have 1 degree of freedom. Right? So I kept that in there. And so, because remember, what we're going to have is group 1, group 2, category 1, category 2. Right, so this is a 2x2 table. So the number of rows is 2, and the number of columns is 2. Right, so for a 2x2 table, then our degrees of freedom is 2 minus 1 times 2 minus 1. I keep wanting to do multiplication there. 2 minus 1, there. Which is 1 times 1, which is 1. My favorite kind of math. 2 minus 1 times 2 minus 1. It's pretty good. Right? Eureka moments. So that's why for this course, right, we're always going to have 1 degree of freedom, which, I mean, do you need a table? No, but you need to know that there is a table for it, right, for finding, for using chi-squareds. And so you can have more than a 2x2 table, of course. And we're just going to look at it and see how it behaves. So you know what I want to do? I'm going to steal a snapshot here. For chi-squareds, for chi-squared tests, we don't find a p-value. Yay. But also, what are we supposed to do, right? So for chi-squared tests, we do not find a p-value. Instead, we're going to find a critical value. And what you'll find is that it's actually a lot easier. Okay? So instead, we find a critical value. Okay. So what happens is that, okay, if we've got, so a chi-squared kind of, and you can see it on your table that I gave you, kind of looks like this. It's a skewed distribution. So this is a chi-squared distribution. And what's going to happen is the numbers on this number line here, they're going to change depending on your degrees of freedom, but the idea stays the same, right? And so what we're going to do when I say find a critical value, what we're going to do is we're going to force this area to be, alpha equals 0.05. Like that's our default. Okay. So then we use the table. We use the table with degrees of freedom equals 1 for this course, right? But same thing goes if you have a bigger table, right? Say you have a 5x6 table, you've got more degrees of freedom, right? 5 minus 1 times 6 minus 1, who knows? Yeah, probably 20, right? And so then you have 20 degrees of freedom. So that's what you would use on your table. But for us, we've got 1 degree of freedom. So we use the table with degrees of freedom equal to 1. And on the table that I gave you, p equals 0.05. Essentially, we're forcing the p-value to be 0.05. Okay. So it's a little bit in reverse, but then we find the chi-squared, right? So then we find the chi-squared value that makes that happen, right? Then we find the chi-squared value that gives a p-value equal to 0.05. Okay. Any chi-squared that we've calculated that's beyond that point, right? So larger than that critical value, we're going to reject the null hypothesis. Because it's the same idea. After this point, the p-value is going to be less than 0.05. Oh, we're past that point, so my p-value is less than 0.05. Right? So it's the same idea, just a little bit different. So any chi-squared value that we calculate that is beyond the chi-squared critical value from the table lets us reject H naught in favor of HA. So I pasted this little tidbit from your table, right? So we said for this course, right, we're only going to be dealing with 2x2 tables, which means we're always just going to have 1 degree of freedom, right? And so really you only need the top row of this table. And so I'll just underline it here. I got to make it bigger though. So then, right, P, you can think of that as your alpha level. Right? And so what we're saying is that, okay, at an alpha level of 0.05 and 1 degree of freedom, any chi-squared that we calculate that is beyond 3.84 means that we can reject the null hypothesis, right? Because that means that the area in the tail, so look at 5.02, right, the next one over, the area in the tail for that guy is 0.025, that's less than 0.05, right? So we've moved far enough out that we can reject the null hypothesis. Right? So same idea, just a different way of looking at it. Oh yeah, so here, if you're looking at, so we got 3.84, that's our threshold. Anything larger than that we calculate, we can reject the null hypothesis. For example, if we calculate a chi-squared of 5.02, that's on the table, right? So it's nice to look at. And so 5.02 has a 0.025 p-value, right? That 0.025 p-value is less than 0.05. So again, by the p-value approach, we would reject the null hypothesis. So I'll draw it out here. In this class,
3.4 and above or above?
and above, yeah. It's very unlikely that you'll get exactly 3.84, but yeah, if you do, that's weird, but also, yeah, just reject the null hypothesis. Unless it costs a ton of money, then don't. Yeah, because it's like, so in this class, we will always have degrees of freedom equal to 1, right? And we use a default alpha equals 0.05. Okay. Therefore, the critical value is a chi-squared equal to 3.84. This means any chi-squared that we calculate that's larger than 3.84, that is larger than 3.84, means we can reject H naught. And I'll put in brackets here, since the p-value would be less than 0.05. Since the p-value P-value, remember, is the area in the tail, so I'll put a bracket inside the bracket. I know, English is not my thing. So since the p-value, the p-value is the area in the tail. So since the p-value is less than 0.05, which was our original kind of decision tree. If the p-value is less than 0.05, you have enough evidence to reject H0. Okay. So what that looks like, if we're going to draw it out, right? So we've got this chi-squared distribution here. And we've got this critical value, chi-squared equals 3.84. Which means that the area in the tail here is 0.05. Right? P equals 0.05, which is our alpha. Oops, got rid of all my stuff. So that's from the table. If we're thinking about, okay, let's say, if we calculated chi-squared equals 6, right? 6 would be somewhere here. We're thinking of it as a number line. The area in the tail for 6, well, I don't really care what it is. I know that that's less than 0.05, right? Because at 3.84, it was 0.05. We forced it to be 0.05, right? And so we use that, that fact. Right? If you wanted to have an idea of what it might be, and this is kind of going beyond, right? But if you want to have an idea for this p-value, right, kind of a range, then what you can do is you can look at the table and say, well, at 1 degree of freedom, right, because we're going to assume we only have 1 degree of freedom, well, 6 would fall between 5.41 and 6.63. So then I've narrowed it down so that my p-value is somewhere between 0.01 and 0.02. But as long as you understand the critical value approach, right, anything beyond this point, reject H0. Okay. Then that's good. So just to clarify, and I've run out of here, in this region, you're going to reject H0. Right. Anything beyond that point, reject H0. In here, we fail to reject H0 up until that critical value. Nice. Any questions about that? This is the same idea as when we said, well, any t beyond plus or minus 2, you can reject H0. 2 is our critical value, right? Plus or minus 2. Critical value, anything beyond that point, reject H0. So it's the same idea. Okay, cool. Cool. There are some situations that we kind of need to be aware of. It's more for completeness than anything else. But it kind of leaks into our assumptions as well. Yellow was a bad choice. Here. Could you even see the... You can sort of see what it says, but anyways. So for a chi-squared, there's a couple of assumptions. Most of them have to do with sample sizes, right? So we have to have enough counts in each cell in order to do the test, right? And so the first thing that we check is that we have to have at least an expected value of 5 in each cell in order to keep going, right? If you don't, use the Fisher's exact test, right? So there's a test for that. There's always a test for that, right? And so, so we check these assumptions, and if it doesn't work out, it will. For us, it will, right? But we still have to check them. And so, so when at least one cell in your 2x2 table has an expected value, and we haven't talked about how to calculate those expected values, but we will, less than 5, then use the Fisher exact test instead. And then kind of getting nitpicky, when a cell has an expected value of more than 5 but less than 10, right? So again, we're talking about these expected values. Then you need to use a Yates continuity correction with the chi-squared, but this is usually done by the software, right? So the software kind of checks it and says, oh, I need to apply this continuity correction. So usually applied by the software. If necessary. So it's not something that we're going to talk about how it's done or whatever, but it's more if you see output and it says, oh, I used the Yates continuity correction, then you kind of, oh, I remember talking about something like that. And then you can look it up, and I don't know. We're just making you better Googlers. And then finally, if the samples are not independent, oh yeah, Yates. Well, yellow is a poor choice. I didn't think it would be so dark, light. I don't know. I don't know what the problem is, I guess. So if the samples are not independent, right? So if it's possible that someone in one of the counts can also be in another count, then that's an issue, right? Especially if you know that the counts are going to be kind of duplicated. Then you use the McNamara test, but not something that we're going to talk about. This is more to expose you to, well, these are some things that we need to check for. Here are some alternative options, but not something that you need to be able to do. All right. So, therefore, when doing a chi-squared, we need to check that the expected values are basically more than 10, right? We're expecting to see more than 10 in each group, or more than 10, bless you, in each cell. Basically saying large enough sample size. It's essentially what it's saying. And make sure samples are independent. Let me go grab the next slide here. Just a stretch. So more of a summary, right? But so the chi-squared, if the results have a significant p-value, right? If our calculated chi-squared is larger than the critical value, the null hypothesis is rejected, and significant differences implied between the groups exist. This is for a test of independence. One thing to keep in mind is that for chi-squareds, it will only tell you if there's a difference, right? So what that means is it will only tell you that there's a difference in the groups. It won't tell you what that difference is, right? And so what we do is, okay, well, if we know that there's a difference, then we can go and dig deeper and figure out what those differences are, right? So that's up to us. But it just does. So imagine you've got, I don't know, 20 categories by 20 categories. You don't want to be manually looking at these and kind of having a feeling that these groups are independent of each other. That would be insane, right? So what you would do is you would run a chi-squared test on this 20 by 20 table. It would tell you if there is anything to be found in there, right? Otherwise, you're just wasting your time, right? So if you find that you're not rejecting the null hypothesis, then you can just say, well, they're all the same. Great, I didn't do any work, right? If it tells you, well, actually one of these is not like the other, then you have to go in and there's other tests that you can do, kind of pairwise comparisons usually, right? And so, so it can be used to examine more than two groups, but does not tell you where the differences are, right? And so would need to be done I'm trying to avoid writing the word separately because I always spell it wrong. But here it goes. Separately? Separately?
I just figured that out this evening. There you go. Yeah, that's right.
How about and there's no spell check on here. Slash separately. I'll do a proper I don't know. It's the first one? Then I'll do this. It's the first one? See, it did a little auto-correct red underline. No, I did that. Anyways, doesn't matter. It wasn't until I was in my undergrad that I was like, definitely is D finitely. I was like, but that's math. I don't know. Just hit me. So anyways, then if it tells you, hey, there's a difference here, right? It's more of an overall blanket check then you have to go in and check them all separately. Okay.
I have a question.
Yes?
So if it's just like, if this test is just making us know the difference between the two groups, don't we do that though with like t-test?
But the thing is, now we're dealing with categorical data. So it's the exact same idea, except we're going to have counts in each category, right?
Okay.
And so we can't talk about the average count because we want to talk about the count in group 1 and the count in group 2. So here, I'll throw this in here. So what we're going to have, right, is we're going to have something that looks like this. Yeah. So like I said, we've got group 1 and group 2, and then has the condition, doesn't have the condition. One rule of thumb is that we put our dependent variable in the rows and our independent variable in the columns. Independent variable, right? But our variables now are categorical, and so we've got 2 categories for each of these because we're only dealing with 2x2 tables. So we've got group 1, group 2. They either have the condition or they don't have the condition. Right? And so how I think of it is if you're talking about groups of people, right? So males, females, those will be the dependent variable because typically we want to see, okay, well, is the gender, does it depend on what group we're in? Right. Have a dog, don't have a dog, that kind of thing. Right. So we're going to have cell A, cell B, C, D, and then to help with our calculations, right, we're going to have our totals in terms of A, B, C, D. Okay. I'll put this on your formula sheet, right? So it's going to be in this way. I'll probably steal this exact image, but make the totals not yellow, probably. Not very good. And so what we want to know is, are the counts in group 1, right, across the columns, are they independent between the 2 groups? Group 1 and group 2. All right. Good. Oh. Wrong. So here, let's talk about what the actual formula is, what we'll actually be calculating. It's huge. So your chi-squared is going to be, so this is summation notation, and so you're going to read that as the sum of, and then everything that's inside the brackets, which is everything. Throw some more brackets on there. So the observed is the count in each cell from the sample, right? That's what we observed. And then what we're going to do is we're going to calculate the expected count. Expected count, right? If these things were the same, right? If these 2 groups are the same, then we're expecting to see this many in this cell. You're going to do the observed minus the expected, and then square those values, making it positive, and then divided by the expected. Right? Feels like a standard deviation formula, and it kind of is, right? How far are the observed values from the expected values? And then once we have those for each of the cells, then we're going to add those up. Okay. And then to calculate these expected values, and I'll put this on your formula sheet as well, of course, your expected value is the row total, right? Remembering that the rows go across, right? So the row total times the column total for each cell, right? And then divided by the grand total. Okay. So each cell is going to have a different expected value, and it depends on the totals that we're seeing for each of those cells. Okay. All right. So that's how we calculate it. Let's do an example. So I guess I'll make it a little bit bigger. Oops. All right. So here's our little example, kind of a run through of what we're going to do for all these chi-squared tests, because we are doing the calculations by hand this time. So we want to know, is there a difference in the exercise habits of male and female graduate students? And so a study, I made this up, but whatever. A study of 32 males and 36 females found that 19 of the males exercised more than 3 times per week, and 12 of the females exercised more than 3 times per week. Leaving some gaps, right? But we have enough information to make our 2x2 table, right? And so kind of our first step to analyzing this is we're going to make our 2x2 table. Like I said, typically the human groups that we're talking about are the dependent variables, right? So they go on our in our rows. And so we've got males and females. And we're talking about, so our categories are if they exercise more than 3 times a week, and then the opposite of that is they didn't, right? More than 3 times is just 3 or more, everything else, right? And so everything on the opposite end is less than 3 times per week. So more than 3. And the other category is less than 3. What we want to keep track of is that we also need our totals, right? Because our expected value uses the row and the column totals and the grand total. So we've got our totals here. So overall, there were 32 males, which means that the total for the males, right, going across the rows, 32. And then 36 females. And they found that 19 of the males exercise more than 3 times per week. And so we've got a count of 19 for the males that exercise more than 3 times per week. And then 12 of the females exercise more than 3 times per week. Okay. We have enough information here to figure out what the rest of the totals and things are, right? And so because 19 plus blank has to equal 32, right? So 32 minus 19. So I've Martha Stewarted the answers here. 19 and 13. Right. I'll use light blue just to indicate the new ones that we've calculated. Right. 12 and 24 make 36. Doesn't help that I switched my rows and my columns on my cheat sheet. So now I have to figure it out. Not that bad though. So then 19 plus 12 for the total for more than 3 times per week is 31. And then 13 plus 24 is 37. So our total sample size, our grand total is 68. Right. What you'll find is that the total for 32 and 36 is 68, but also 31 plus 37 is 68. Because we've got 68 people and they can each be put into a gender category and an exercise category, right? So they should add up to the same number. Okay. So now we're ready to start our hypothesis test, right? So step 1, state our hypothesis. Or hypotheses, if you want. So just as a little side note, right, we said that this is our dependent variable and the exercise frequency is our independent variable. So our null hypothesis is that the gender is not significantly related, right? So there's no association, right? If they're not related, they're independent, right? And we're doing a test of independence. And so gender is not significantly related to exercise frequency. Right. Gender, I'll just put in brackets, gender is independent of exercise frequency. And vice versa. And vice versa. We're doing a test of independence. Just by looking at these counts, right? 19 out of 32 versus 13 out of 32. And then 12 out of 36 and 24 out of 36. Right, so we expect to see, or we suspect that there is some imbalance there. Right? But we'll see. Chi-squared test will tell us. Right. All right, so our null hypothesis is that they're not significantly related. And so our alternative hypothesis is just going to be the opposite of that. Right? In all our chi-squared testing, we're using a 2-sided test, right? We just want to know, is there a difference, right? Because what we said was, it won't tell us what the difference is. It'll just tell you if there is a difference, right? So gender is significantly related to exercise frequency. Just the opposite of your null hypothesis. Okay. So then, once we have our null and alternative hypothesis, we can go on, and our second step, which is kind of a fake step in my mind, right, is we're going to determine our significance level, right? Pick our alpha level, but also in that step now for the chi-squared, I'm also going to say what the critical value is. Okay. It's always 3.84 for us. So step 2 is to determine the significance level. So we will assume alpha equals 0.05 with degrees of freedom equal to 2 minus 1 times 2 minus 1, which is 1 times 1, which is 1. Showing way more work than I need to, but just so you know where it came from, right? The number of rows minus 1 times the number of columns minus 1. So with 1 degree of freedom, therefore our critical value is chi-squared equal to 3.84. I'll put in brackets from the chi-squared table. So step 3, can't remember what their steps are, but I guess I could scroll to the top. But I feel like it's determine the test that you want to do. Pick a test, any test. No, not any test. Chi-squared test. So to test for independence, oh, I guess I should say what the step is. Determine the test. To test for independence between groups we will use a chi-squared test. So now we have to check assumptions as well. Well, first assumption is that we have to have a categorical variable or 2 categorical variables. So categorical variables oh, I'm going to scoot this down. Beep. Yes. Gender and exercise frequency are categorical. So that's good. The thing about assumptions and why I think I get annoyed with them is because we'll always check them, but they're always going to pass. Or even if they don't, then we'll just argue that we can ignore that assumption. So we just say, oh, well, sorry, the sample sizes weren't big enough, but we're going to assume that they're representative of the population anyways. Right? So assumptions are kind of, I don't know. I don't like them. But when it's things like, do you have a categorical variable? Yeah, that's good to check. Expected values must be larger than 10 for each cell. What does that mean? That means that we have to find our expected values. Find expected values. E is the expected value. Let's just denote that by E. E is the row total, just summarizing from earlier, times the column total over the grand total. So what we do is we copy our data table, right, our 2x2 table from the sample, and we only keep the totals, right, to figure out what the expected values are. And so here's our 2x2 table. We had males and we had females, and we had our totals. And we had more than 3 and less than 3. And then we've got our totals. So our totals, our grand total was 68. The total males was 32. Total females was 36. For more than 3, the total was 31. And for less than 3, the total was 37. So now, I'll use a different color for the ones that we calculated, right? But for this first cell, the males that exercise more than 3 times per week, if we have 32 males and it's the same, right, then we would expect to see, sorry, no worries. I actually think it's pretty funny. People get really embarrassed.
No, I can't be no, I guess we don't need that.
It's like, I really got to go. Okay, but just one more thing. So 32 times 31 for this cell, divided by 68. How about I just steal it from here without calculating it? Oh, but I've got them all swapped around. 14.59. Gonna lock that in, but I'm also gonna check. Because I didn't put labels on my Martha Stewarted one, so. Oh, I can't see squat. 31 times 32 divided by 68. Great. I picked the right one. For the males less than 3, right, I've got 32 times 37 over 68. 32 times 67, or 32 times 37 over 68 is 17.41. Oh, because it's the row totals times the column totals, right? So we only care about the totals, and then we're going to leave the data that we actually collected for later, right? Because those are our observed values. And then we've got, for the females, we've got 36 times 31 over 68. So we're expecting 16.41. And then finally, we've got 36 times 37 over 68, which is, which one here? 15.5, or sorry, 19.59. Let me check those. $36 times 37 divided by 68. Yeah. Also, notice that 16.41, looking at the females, plus 19.59 equals 36, right? So these expected totals are still going to add up. They're all going to work out if we've rounded properly, right? Or might be 0.01 off or so by rounding, but that's all right. And so now we've got our expected values. If the number of times that we exercise per week, right, is independent of the gender that we're working with, no, the gender that we have, then these are the expected counts that we would see, right, with these sample sizes. So now, you know when a hair just catches your eye? Just grabbing at things here. Okay, so why did we calculate these? Right, it was to make sure that all our expected values are more than 10, right? And so we look 14, 17, 16, 19, phew, right? We can go ahead and assume that the chi-square test is fine to use. Right. All expected values are more than 10. So the chi-squared test is appropriate. The last assumption, remember that thing I mentioned about, okay, well, someone in one of the cells shouldn't be able to be in a different cell as well, right? So all these groups have to be independent of each other, right? And so a female can't be in the more than 3 times per week and the less than 3 times per weekend, right? So we can, and if you're female, then you can't be male, right? And so all these are independent. So I'll just summarize that as all the counts in the cells are independent of each other. And so that's an assumption. That's it for that assumption. Great. That was what, step 3? Now, step 4. Step 4, I'll call it do the test. This is where we actually calculate the chi-squared. Right? And so remember that the chi-squared is the sum of our observed minus the expected squared over the expected. Right. So what we're going to do find this for each cell. Then add them up. So whenever we have summation notation, fun to say, fun to do. Summation notation, we've seen it before with the standard deviations and things like that. We do everything that's inside for each cell, right, or for each data point, and then we add them all up. Okay. So what I'm going to do is I'm going to make an extra big 2x2 table because I'm going to do the observed minus expected squared over the expected in each of the cells, right? So I want to give myself lots of room. That's more as a heads up for you if you're doing it here. And so we've got our males and 1, 2, 3 females. We've got more than 3 and less than 3. I don't need the totals anymore. So what I'm actually going to do is I'm just going to scoot this guy, the less than 3. I'm going to scoot it all the way over. Whee! Scoot it over a bit more. Give myself a bit more room. Right. Those totals, we needed them to find the expected values, but now we have those, so we don't need them. Okay. So in each little quadrant, I'm going to make a note to myself what the expected value and what the observed value was. You don't have to do that, but it's just easier for me to see stuff, right? And so I guess I'll start with the observed value, which was, I've got them all switched around here, 19. And then we found our expected value, which was 14.59. The males with the less than 3 was 13. And the expected was 17.41. For the females, we had an observed of 12 and an expected of 16.41. Really hope I didn't read these wrong this time, but that's okay. Observed of 24, while the expected was 19.59. So then, if we do the observed minus the expected squared over the expected, we get 19 minus 14.59 squared over 14.59. Oh, I wrote it too big, but I'll learn from my mistakes. Steal it from here. I get 1.33 for this one. But check it because, like I said, I'm jumping around here. Thank you. So doing the same thing here, observed minus expected squared over the expected. 13 minus 17.41 squared over 17.41. 1.117. Moving down to the females, observed minus expected squared over the expected. You don't need to write out the formula or anything like that, but I find that it's helpful to map out where to put stuff. So I get 12 minus 16.41 squared over 16.41. 1.185. And then finally, 24 minus 19.59 squared over 19.59. 0.993. Okay, I'll just highlight these values here. So then, if our chi-squared is the sum of our observed minus expected squared over the expected, that's going to be 1.33 plus 1. Sorry, not 11. Yikes. That would really mess up our chi-squared. 1.117 plus 1.185 plus 0.993, which I've stolen is 4.628. Oh, we did it. My 8 looks wonky. There. Still wonky, but the other one. So now, right, for our final step, right, this was step 4. Step 5 is our conclusion. Yeah, you bet. And if you decide to compare your calculated chi-squared to the critical value in step 4 or step 5, it doesn't matter. But I'm going to use it as part of my conclusion, right, to kind of say, this is why I'm rejecting the null hypothesis, right? And what does that mean? Okay. So, our conclusion here, since our calculated chi-squared equals 4.628, I always want to boost my claims with actual numbers, right? So you don't just want to say a generic, since my calculated chi-squared is larger than the critical value, right? You want to say since 4.628, right, which is my calculated chi-squared, is larger than the critical value of 3 point whatever, can't remember, 3.84, then we can reject H naught. And what does that mean for this question? Right. So since our calculated chi-squared equals 4.628 is larger than our critical value, which was chi-squared equal to 3. What did I say, 84? Yeah. Can even throw in 1 degree of freedom. Why not? Heck. Alpha equals 0.05, 1 degree of freedom. Show off even more. It's stuff that we know, so why not put it down? So is larger than our critical value of 3.84. We have enough evidence to reject H naught in favor of HA. So like I was saying, if you put this blurb as part of doing your test, or if you put it as part of your conclusion, it doesn't matter, but this is the next step. Our conclusion has to be in terms of the actual question, right? And so we have to scroll back to the actual question. Is there a difference in the exercise habits of male and female graduate students? Yes, there is. Done. Well, we just rephrase the question as an answer, and then we're done. So in fact, I'm going to steal this, copy, but also we can look at our boring alternative hypothesis. Gender is significantly related to exercise frequency, but it's just nicer to rephrase the question as an answer. They should be saying the same thing though. Yeah. And so if we remember the research question was this. Yes, there is a difference in the exercise habits of male and female grad students. Yes, grad students. Nothing to it, right, guys? Just follow the steps. Not too bad. All right, so that's our whole example. Let's see if I had anything else in my. Oh, and then the last. Any questions about that example, chi-squareds, life? No, don't ask me life questions. Well, you can. All right. No questions? Chi-squareds? No. So you have to email me your group assignments by 9 o'clock tonight. What's nice about having class in the morning is that now you've got more time during the day. And like I said, I'm here all day. I'll be here during our regular class time too, but I'll just be in my office, right? So I'll be in my office, which is C104, all day today. So I got stuff to do. So for next week, you've got your quiz. We settled on that, yeah? Good. And then read chapter 10 for next week. But I'll walk you through it, so I'd rather that you focus on quiz too. Yeah? All right. So you're gonna email me your group assignments as a PDF, CC your group by 9 o'clock tonight. The time is yours, unless there are questions. Yeah, I might make you do a little one for the quiz. Feels likely, because we spent half the day doing it. So you will do a chi-squared calculation for the quiz. But I'll give you the formulas.
Is it just one?
Yeah.
Oh, okay. So you have that one.
Yeah. Yeah. All right.
I'm really confused with what equal variance is. One does say equal variance.
Let me just end this recording here.